Section 7.3, Special Products of Polynomials. A product is just the result of a multiplication problem. So any of the problems that you're going to see here could be solved by using the FOIL method, the fake Punnett square method, the vertical arrangement, the distributive property, any of the methods we talked about in the last section for multiplying polynomials. But these are three special products, so we have shortcuts to immediately jump to our answers after seeing the original problem. Now this first one is a plus b squared, which it might be easiest if we write it out as one set of parentheses, a plus b, times another one, a plus b, because after all, that's what squared means. It means something times itself. To simplify this, I'm just going to use the distributive property first with my a. Now, a times a is a squared. A times b is plus ab. Now I will distribute my b to the other terms in the second polynomial. B times a is ba, or I can rearrange that to make that ab. And then finally b times b is b squared. You'll notice that these two terms in the middle here can combine, and I can actually get my simplified version, which would be a squared plus 2ab plus b squared. And that's a nice formula that we can jump to right from this, regardless of what a and b are. I'm going to use the same type of process for the second one, a minus b squared. I'm going to write out as two sets of parentheses, a minus b times a minus b. Once again, use the distributive property. A times a is a squared. A times negative b is minus ab. Now when I distribute, I have to make sure I distribute the negative along with the b. Negative b times a is negative ba, or negative ab. And then a negative b times a negative b actually brings it back to be a positive b squared. Once again, you'll notice that these two terms in the middle combine as they are like terms, and I can get my simplified answer, which is a squared minus 2ab plus b squared. Once again, something I can jump to right away, regardless of what a minus b is. I'm now going to look at my last example, a plus b times a minus b. Now this is already set up very well for me to use the distributive property. I'm just going to rewrite it over here, a plus b times a minus b. And once again, distribute. A times a is a squared. A times negative b is negative ab. Distributing the b. B times a is ba, or positive ab. And b times negative b is negative b squared. For the third time in a row, my middle terms are going to combine, but this time they cancel out as opposed to combining to make a coefficient of 2. Since the coefficient is 0, I don't even need to write it when I write in my final answer, which is a squared minus b squared. Now, these are the three special products of binomials that we're going to look at. We'll eventually look at other special products that involve some trinomials, but for now we're looking at multiplying two binomials that are the same, either a plus b or a minus b, or two binomials where they're the same numbers or expressions, but one is being added, one is being subtracted. And each of these actually have special names. The first two are called perfect square trinomials, because I squared something and made it into a trinomial. Not a clever name, but it's one that we can use. The third one is called a difference of squares. Difference meaning a subtraction, which is what I end up with, and squares because my only two terms that remain are perfect squares. These are the three special products that we're going to use. Now let's put them to work. Here's a little practice with some perfect square trinomials. I've got the formulas above them. What we're first going to do, when we have 3x plus 4 squared, we recognize this plus means that we're using this formula because it's a plus b. And I just want to identify what is a and what is b. Well, a is my first term, which is 3x. b is my second term, which is 4. And now I can just plug right in to this part of my equation. A squared is 3x squared. I'm going to put that in parentheses. Plus 2 times a is 3x, b is 4, plus my b squared is 4 squared. And now I just simplify each part. 3x squared is 9x squared, because that's 3x times 3x. Plus, multiply 2, 3x, and 4 is 2 times 3x is 6x, times 4 is 24x. And finally, 4 squared is a positive 16. And if we've done this correctly, we won't have anything left to combine. That's going to be our final answer. Same process on the right when we have a minus to begin with. We have a minus, we're going to be using this formula here, the a minus b squared. Once again, I'll first identify my a, which is 5x, and my b, which is 2y. We don't need to identify it as a negative 2y because we're using a minus b. So we're saying we're subtracting b. We already accept the fact that it's going to be negative. My b is just 2y. Now let's plug into our formula. That's going to be a squared, which is 5x squared, minus 2 times 5x times 2y. My a and my b. Finally, plus my b, which is 2y, and I need to square that. 5x squared is 5x times 5x, which is 25x squared. Multiply everything else in that middle term. Negative 2 times 5x is negative 10x, times 2y is going to be negative 20xy. Even though they're not like terms, I can multiply them. I just can't add them or subtract them. And finally, I have 2y multiplied by itself, which is going to give me a positive 4y squared. And that's my final answer for this one. It's a lot shorter than using FOIL or any of the other methods, and it's a nice shortcut to get to our answer pretty quickly. Here are 2 practice problems for you to try. Pause the video, try them out by yourself, and then resume the video so that you can see the work and the final answer. Alright, and so here are your final answers. On the left, we end up with x squared plus 10x plus 25, and on the right, we get 4x squared minus 12x plus 9. Feel free to pause the video, double-checking your work if you got something different. Now we're going to move on to the difference of squares. This is where you have the same 2 expressions in each binomial, but in one they're being added, and in the other they're being subtracted. So we have t plus 5 times t minus 5. Just like before, I can identify my a, which in this case is t, and my b, which is going to be 5. And now it's just a matter of plugging into my formula, which is a squared minus b squared. So I'm going to get t squared minus 5 squared, keeping my parentheses. And now I'll just do that out. Well, t to the second power is just t squared. 5 to the second power is 25. Wow, amazing how quick that works. And we showed on the first page why it works. We don't need to do out the FOIL or the distribution property every time. We don't need to worry about that. Let's try it again on the right. In this case, you'll notice that I'm starting with my 3x minus y instead of starting with my plus y. It doesn't make a difference. Because multiplication is commutative, I can still identify my a to be 3x and my b to be y. And now I'm just going to plug in to my formula. 3x squared minus y squared. Squaring each one, 3x squared, 3x times itself is 9x squared, minus y to the second power is just y squared. Both of these result in differences, meaning subtractions, of perfect squares. T squared and 25 are both perfect squares. 9x squared and y squared are also both perfect squares. And that's how easy this one is. It's really nice. So now you can give it a try. Here are 2 examples using difference of squares. Go ahead and pause the video, do the work, and then compare your work and final answer with what is shown. Alright, and here we see our two answers, x squared minus 9 and 4x squared minus 9y squared. Now, going forward, you don't have to write out what a and b equal each time. If you can jump right to your answer, that's fine. These are designed to be shortcuts. I just put them in here for now as something that will help us learn what the formulas are and how to apply them. But as long as you can use them, that's really what's important. While it may seem that these special products don't really have much benefit for us, one way that we can use them is to actually make mental math a little bit easier. Thinking about what I have here, I've got three problems, 107 squared, 47 squared, and 26 times 34, that all seem like kind of a pain to do out, especially without a calculator. But we can use these special products, if we think about it, to make it a lot easier to do. Think about 107. If I wanted, I could write that as 100 plus 7. And now when I square that, I can recognize that this is a special product, a plus b squared. Where 100 is my a and 7 is my b. Well, if I remember the formula correctly, I can just plug in and get numbers that are a lot easier to work with. I know that I'm going to have 100 squared plus 2 times 100 times 7 plus 7 squared. And these are actually a lot easier. 100 squared, well, that's a 1 followed by 4 zeros, or 10,000. 2 times 100 times 7 is 200 times 7, which is 1,400. And 7 squared is 49. These are very easy to add because nothing actually gets in its way. We've got 11,449, which is exactly what 107 squared is. So that's one of the ways that we could use a perfect square trinomial to figure that one out. With 47 squared, we could maybe choose to use the other perfect square trinomial and rewrite this as 50 minus 3 squared, which I hopefully recognize as a minus b squared, where 50 is a and 3 is b. Now, going into my formula, I would just make this 50 squared minus 2 times 50 times 3 plus 3 squared. Each one of these is actually very easy to do. 50 squared, or 50 times 50, is 2,500. Minus 2 times 50 times 3, well, negative 2 times 50 is negative 100, times 3 makes it negative 300, plus 3 squared is 9. Pretty easy to do this here. 2,500 minus 300 is 2,200, plus the 9 equals 2,209, which is exactly the same thing as 47 squared. And finally, another way that we could do this is we could look at 26 times 34 and recognize that 26 and 34 are both the same distance from 30. They're both 4 away. 26 is 30 minus 4. Meanwhile, 34 is 30 plus 4. What I could recognize here is that this is a difference of squares. This is a minus b times a plus b, which remember we said was exactly the same as a plus b, a minus b. 30 is a, 4 is b. I can now plug into my formula, which is a squared minus b squared. That's going to give me 30 squared minus 4 squared. Well, 30 squared is 900, 4 squared is 16, and 900 minus 16 is a lot easier than doing 26 times 34. It's just 884. which is exactly what you get if you do 26 times 34. Now, what's the point of these three things? Well, it's the type of mental math that I try to do when I'm trying to solve a problem up at the board. Sure, there are calculators available, but sometimes it's nice and somewhat satisfying to be able to do these problems in your head by moving some numbers around and being clever about the way you write them. So that's all the real benefit is here. Coming up with these expressions here, you have some leeway. You could write them different ways and use different rules, but it's just an option. These are probably the most convenient ones to choose based on the numbers that we started with. So there you go. Now let's just look at a real-world application to using these special products. What I have here is a Punnett square, an actual Punnett square from an actual biology situation, not like the fake Punnett squares we've been using to multiply polynomials. Take a second, pause the video, and read the description of the problem now. After seeing that and looking at the diagram, you can see a very clear answer to question A. What percent of the possible gene combinations result in black patches? Based on the fact that we have 4 total little boxes and 3 of them represent black patches, whereas only 1 of them represents red patches, we know that the percentage would be found by doing 3 divided by 4, which is equal to 75%. So 75% of the possible gene combinations result in black patches. Now, how could we use a polynomial to model the possible gene combinations? Well, you have to think about it this way. From the first parent, there's a 50% chance that they're going to give the dominant B gene. And there's a 50% chance they're going to give the recessive R gene. And that's actually true from both parents. So since I have that happening twice, I could square this, representing the 50% chance that each parent has of passing on the dominant gene and the 50% chance that each parent has of passing on the recessive gene. Now, I hopefully recognize that this is one of my perfect square trinomials, a plus b squared, where a is 0.5b and b is 0.5r. By plugging into the formula that I used before, this is going to give me 0.5b squared plus 2 times 0.5b times 0.5r plus 0.5r squared. Now, to simplify this expression, I have to multiply 0.5b times itself. Well, if I think of 0.5 as 1/2, I might find it easier to do 1/2 times 1/2, which is 1/4 b squared. And if I look at 2 times 0.5b times 0.5r, 2 times 0.5 is 1, so I'm left with the 0.5, or perhaps 1/2 br. And then my last term is very similar to my first one, which is 1/4 r squared. Now what you might notice is the coefficients actually correspond to the gene combinations in our Punnett square. 1 out of 4 is b squared, or bb, this one right here. 1/2 is br. Well, these BRs here represent 2 out of the 4 possible combinations, and 2 out of 4 reduces to 1/2. And finally, 1/4, or 1 out of 4, are the gene combination RR, the homozygous recessive, which gives us the red patches. And so this expression allows us to model the gene combinations and the frequency with which they occur. It's a wonderful combination of biology along with mathematics that I hope you find helpful going forward.